So very exciting. Here is our first factor that affects charge stability, and that's electronegativity of the atom that bears the charge. This is a periodic table trend. It is strictly a horizontal periodic trend. We'll have another video that tries to clarify that. So let's move across the periodic table. Let's see. Let's start with carbon to nitrogen to oxygen to fluorine. We've moved across the second row. And let's draw molecules that are based around these atoms. So we have methane. We have ammonia. We're simply taking these atoms over here and making them the central atom. Our good friend water, and then HF. So these all in theory could react with a base, and we'll keep using water. Not very realistic for all these examples, but some kind of base. And water could react with all four of these molecules and set up, I've shown one way, this is a reversible process, set up an acid-base equilibrium in which the water as a base has a lone pair. That lone pair abstracts these electrons, the hydrogen, and deposits that CH bond or NH bond, OH bond, or FH bond on the central atom. So we get this. Plus H3O plus. I'm not going to write H3O plus all the time, it just slows me down. But if we were balancing the equation, we'd do that. Might as well just put dittos there. Plus hydroxide is the conjugate base, and then fluoride is the conjugate base in this case. Ditto, ditto. Great. So these are all very nice acid-base reactions, and they all could possibly occur. However, some of these are more favorable than others. And as it turns out, if you look at the pKa for methane, this is approximately 50. Now 50 is a really high number. This is actually a very weak acid. And if we write in the other pKa's, ammonia is around 35, water is maybe 16, and HF, I've got to cheat and look at my screen, HF is about 3. So this is relatively strong, HF, and this is relatively weak. Well, why do we observe this trend? We observe this trend. How do we explain the acidity of this molecule, this neutral molecule? We look at the charged species in the conjugate base. This is what we've been discussing. So here is a carbon that's an anion. Carbon is not very electronegative, certainly not compared to fluoride. Fluoride is much more electronegative. Whoops, let's go from HF. So here's fluoride, which is very electronegative. The more electronegative species doesn't mind holding this excess negative charge bearing the anion. So this is HF. F is the most electronegative and therefore forms the most stable conjugate base. And if the base is the most stable, meaning it's the weakest conjugate base, then the HF is going to be the strongest acid. And as electronegativity decreases, hydroxide, this amide, and then this carbanion, these anions become less and less stable. They become more basic. And therefore, this is the parent acid is less acidic. So this is a periodic table trend where as we go across the periodic table, electronegativity increases and the stability of the anion increases, and therefore the acidity of the parent acid increases. So this is an electronegative trend. It's determined by the acidity in this case is determined by the electronegativity of the atom that bears the charge.